Okay, Julio will give us the grand finale of his lectures.
Okay, so maybe because people were asking, and to make sure I mention something before the end in case I don't have time. Okay, just very quickly, what's the connection between this whole kind of semi-classical action and observables? Well, there's many ways of saying it. So for instance, if you go to the usual like canonical book of path integrals in quantum mechanics by Feynman and Hibbs, even in the first chapter, it explains that, okay, these on-shell actions, so if you evaluate the action on the classical trajectory, it's a function of the initial positions or velocities or momenta, and then you can take derivatives with respect to those, and that actually computes various observables, right? There's another way of seeing this. So how do we extract observables from this action, right? So we saw that in position space, in impact parameter space, this amplitude exponentiates, right? So let's try to go back to momentum space, right? So the original momentum space amplitude, how is it related to the position space one, right? I just have to do the inverse Fourier transform. So it'll be something like e minus 2b e to the minus I e dot q. So remember that t equals minus q squared, right? But if this amplitude exponentiates, so this was some function of s and b, right? Then in the classical limit, this thing is very large, right? So this is a rapidly oscillating phase, because we were in this limit where this Born amplitude was large. So this integral is going to be dominated by a saddle point, right? So the saddle point will be when the derivative with respect to the integration variable of the exponent, which is e dot q plus s, is 0. And this gives us a very nice equation, which is q is going to be equal to essentially the derivative of s with respect to b. Okay, but this now was something very large, so now this q is going to be large, right? So this q actually will be kind of the difference between the momenta in the initial and the final state. So this is actually the impulse of the particle, the classical impulse of the particle. And you can try to go ahead, and if you compute this Fourier transform of the trio level amplitude, and you just take the derivative with respect to the impact parameter, how you will recognize that you get the same result as from the equations of motion. Okay, so this is just kind of closing the circle, how to go like from the amplitudes to the observables. Okay, that's part of the story. There's a much nicer story that actually has been fleshed out recently by Jungwook and Sangmin and others, where, okay, so at the end of the day, the S matrix was the generator so the S matrix is just a time evolution operator. So you can also think about this phase, this semi-classical phase, as kind of the generator, the classical generator of time translations. Okay, so I recommend that you take a look at their papers, because they're very nice, and they really explain how you can compute the kind of the time evolution in some scattering process of many observables just by taking various Poisson brackets with this classical quantity. Okay, so this is just the simplest example from the semi-classical approximation, but this contains the information about the time evolution. So as long as you keep enough data about the initial and the final state, you can always study the evolution of essentially any quantity. Maybe I'll have more time to say something at the end about this. However, let's now make the connection with the other two expansions that I mentioned yesterday. So remember, we had this phase diagram for classical dynamics, gravitational dynamics, which had this numerical GR. There was this weak field, which was post-Minkowskian expansions and post-Newtonians. We've already discussed what this weak field post-Minkowskian expansion is, but we haven't discuss expansion in velocity, so we'll do that now. And also the other expansion was the self-force expansion, which was an expansion in the mass ratio of the particles, right? So here we had B over Gm, and here we had M, big M over little m. So my goal now is to first discuss how to see the self-force expansion, and then I'll make some comments about this Pn expansion, so that you're aware of kind of the various techniques and how they relate to the scattering amplitude. Okay, and you'll see that the self-force expansion is actually very simple. And essentially, we've already done it without realizing. So let's think about the kind of mass or like self-force counting. Okay, so let's revisit. So we had this on-shell action at 1 p.m. order, right? What did this look like? This looked like G m1 m2 squared over q squared. Essentially, then there was like, at the second order, we had the same thing, E m1. So actually, let me call them little m and big M from now on, so that everything is clear. But at 2 p.m., we have to have a correction that goes like GMQ, right? So it's subleading to this. So I'm going to choose it to be the big M. And this will have a piece that goes like 1 and a piece that goes like little m over big M. Okay? So earlier we were just calling these M1, M2. So what we found is that the result went like GQ M1 plus M2. Okay? But now we just declare that one of them is much heavier than the other. And then we see that we can think of this quantity as small. Okay, so this would be what's called 0 SF, where I don't have, kind of, in the corrections that describe the dynamics, I don't have any powers of the small mass. And this is first order in self-force, which is the leading correction in the mass. Okay. However, notice that this is symmetric, because I just chose one of them to be the big one or the small one. But we'll see that we can give a nice interpretation to all of these diagrams at each order. Okay. Let's look also at the next one. If I go at 3 p.m. order, now things get more interesting. Okay, so this is going to go like same thing. Now I'm going to have G big MQ squared, which was a log. And now I can have 1 or 2 powers. So this again is going to be the leading order in self-force. This is going to be the first order. This is going to be the second order. But notice that because it's symmetric, this is also the 0th order if I thought this particle and this is the heavy particle. So what I want to do now is to look at which diagrams would contribute to each one of these orders. Okay, so we are going to look at some diagram and try to find and get some intuition for which pieces of the diagram contribute to each order. So we did this for the classical limit. So we looked at some diagram. We did this small q expansion, and we identified the classical piece. Now I want to do the same for this self-force expansion, where we're going to look at some diagram and try to say, okay, this diagram will contribute at the leading order in the mass ratio, or will not contribute at all, et cetera, et cetera. Okay. Okay, so the picture is going to be that, again, we have this scattering amplitude, but now there's going to be one particle which is heavy. So let me just draw it as a double line, which I'm going to write on the top. So this is the one that will have mass m. And then I have the other one, which is light, which has mass little m. And we're going to keep in mind that we already had these counting rules for small q, which also involve inverse powers of the mass. So this will be very useful, because we already have a little intuition of what it means to take a match to be large, right? Because it's the same as taking q being small. So let's try first to write diagrams that we think are going to contribute at the leading order. So at 0 SF, okay, so we're going to start at one loop because, okay, at tree level, there's nothing interesting. If you want, there's here a 1, which is 0 SF, but this is boring because there's only one diagram. So let's start at one loop and try to get an intuition of which diagrams will be of which order. Okay. So, okay, I want a suggestion. There were not so many diagrams. Come on, there was like two diagrams. So, or 3 if you include the symmetric parts. So which one do we think it's going to give something that has like the big mass? So, okay, so here's the clue. We want diagrams that have as many powers of the big mass as possible. Okay, that's what that means. So this diagram has 1 power extra. So this has little m squared, m cubed of the big mass, whereas this one has an extra power of the little mass, okay? So remember, what were our power counting rules? There were only 2 rules that involve the mass. One is that every coupling of a graviton to a particle comes with 2 powers of the mass, and then every propagator comes with inverse powers of the mass, okay? So exactly. So we want as many gravitons attached to the heavy line as possible, right? So let's see. So okay, at tree level, there's only one diagram, so let's just draw it. Right? At one loop, okay. So, for instance, this is promising because we have more gravitons attached to the heavy line than to the other one, okay? And indeed, if we power count these using our rules, so remember, our rules were that here, each one of these vertices has the power of the mass, right? So this goes like m to the 4th coming from the vertices, m squared and m squared. And I have a propagator, which is going to give me 1 over m. And then here I have little m squared. So indeed, this goes like m cubed m squared, which is precisely the same as this. Okay? Okay, the other contribution at this order, in principle, so I told you that those classical contributions in 4 dimensions vanish. But in principle, in here, there's also hidden some correction like that. Because, okay, the leading order in this diagram, right, is the thing that cancel when we exponentiate. But at the subleading order, there could be corrections, right? So the leading order of this diagram went like g m1 squared m2 squared with another power of g m1 m2. So here, now I'm going to write m, 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 m. But I want to look at q over m corrections to this diagram, and which q over m corrections I'm going to add. So I want to remove powers of the small mass, right? So I want to look at the subleading expansion of things like this propagator. So remember, the rules were that these sort of attachments, this goes like m squared 1 plus q over m, and also the propagator itself, right, went like 1 over m plus order q over m corrections. Okay, so there will be a piece hidden in this diagram. So let me draw it like this. Let me just put a dot here to denote that I expanded something along here to subleading order. Okay, so this will also be at this 0 SF order. Okay, so what is the intuition for this? The intuition is that at leading order, we just have this light particle interacting with the 1 over r potential from the big guy. But now, actually, this is generating a full background metric. So this piece here will just be the light particle interacting now with the 1 over r squared potential, which is a nonlinearity coming from the big guy. So you can just think of this as the 1-point function of the graviton, so the metric generated by the big guy. Here we have something different. What we have is this light particle scatters against the 1 over r potential. It deflects. So now its motion, it's modified. So this correction to the propagator you can think of as the particle recoiling. And then it interacts again with the 1 over r potential. Okay, so we can keep going. So there's a general pattern here, which is that, for instance, all of the diagrams that look like this, any number of attachments, then you see that this will always go the same way. So because we have always one more vertex than propagator, right? This is going to have m, but there's divided by 3, right? So this is going to have many, many powers of the big mass. Right? In this case, we have m to the 8 divided by m cubed, and then only 2 here. So this will be some higher PM correction, but definitely it's going to be at 0 SF order. Right? And the other diagrams that are going to contribute are diagrams where we have the same type of fans, so things that look like this, but then with these subleading orders in the small guy, generically. Yes? This, right, so, okay, I was avoiding this, but this is quantum. But at this stage, just with Q counting is a bit tricky to see if how this is quantum. So when I discuss velocity counting, this will become obvious why we don't need to include this. Yeah. No. So naively, it will look classical in the terms of the Q counting, but this is actually a quantum effect. So this is a bit harder to disentangle. Yeah. Yeah. But you see that this loop doesn't know about Q essentially, right? So already you see that there's something funny with these vertex corrections. Yeah. But okay, going back to the discussion here, right? So this whole class of diagrams, the interpretation is very simple. The interpretation is just the light particle traveling in the field of the heavy particle. Okay, so we had this picture of cell force where we said that there's like this big black hole, right? So there's some metric that this generates, and then I have a light particle moving in the background of this, right? So here, notice that we only have like a single graviton hitting at a time the light particle. So we are really just looking at the field of the heavy particle, okay? And what these diagrams are building, well, this is just building the metric. All of these diagrams where I have many attachments to the heavy particle and none to the light particle until the very end. This is just building up the metric order by order, okay? And then this is computing the solution to the geodesic equation secretly. Okay? So this is the light particle recoiling over and over again. And you can just solve the geodesic equation perturbatively in G. And this is precisely what all of these diagrams are doing for you. Okay? So there's no mystery here. At the end of the day, this is just the probe limit at the leading order. There's nothing funny. I just have some unperturbed background and then a light particle moving in that background. Okay, so this can be made even more manifest. So for instance, if I look at this diagram here, we can play this trick that we were playing when we were doing the box diagram, right? So for instance, let me give the triangle as an example since we are familiar with it. So what did this integral look like? This integral looked like ddl, L squared, L minus Q. And if this was like little p, this is big P of the heavy particle. This will be 2p of L plus I epsilon. But then if I average, as before, over the two labelings, so we did this with the box, right? I would have that this is 1/2 this plus 1 minus 2 P dot L plus epsilon. So this again is going to give me, using my favorite identity, something that goes like delta function of P dot L. So this diagram just looks like two static sources that are sourcing each one this metric. Okay, there was also 1 over q squared that I forgot. Okay, so here I just have like these two kind of L minus Q as a static source. So what does a static source look like? Static source just looks like delta function P dot L. Okay, why is that? I can just write this as the integral d tau e to the I P dot L tau, right? And then if I do the Fourier transform of this in L, it just gives me something which is moving with momentum p in a straight trajectory. So it's a source, point-like source, right, which is just traveling at a constant speed, okay, undeflected. So these delta functions that we see over and over again, they have a very nice interpretation, but you can just think as these static sources. Okay, so these diagrams that I was drawing here, you can always play this trick. So these will just become a bunch of static sources, which is the heavy particle, which is undeflected. So at the leading order, we just have this. We just have a light particle moving in the background sourced by the heavy particle. By the way, there's something else that one might notice is that this is just computing the metric, but this is a point particle, so this is a spherical symmetric source. And we know that there's only one solution to Einstein's equation in vacuum with like a spherical symmetry, right? So this is actually going to build up the Schwarzschild metric. Okay? So every time we're computing these diagrams, we're just recomputing over and over again secretly the Schwarzschild metric. So in fact, there's better and more efficient ways of doing this calculation by using the background field method. And instead of expanding around flat space, one can expand around the kind of perturbative background metric, which is the Schwarzschild metric, so we can save a lot of this work. Okay, so this means that 0SF, we figure out, this is just probe. So probe what? So we have the metric, G bar, and X bar, which is the geodesic. So at the end of the day, these diagrams are just computing something that we already know. Okay, so the interesting stuff is at the first order in the self-force expansion. So let's think about that. Okay, so I also want a suggestion now. At one loop. Okay, one loop is kind of trivial, right? Because everything was symmetric. So the only thing that we can have is, okay, so we had this triangle diagram, which was 0SF. So if we just flip it over, now we will have one more power of the light mass, right? So the diagram that now matters at 1SF, first order in the self-force expansions on the large mass ratio expansion will be something that looks like the light particle interacting with the heavy particle, which again, you can think of as some static source. And similarly, there will be this diagram where now I would have the light particle making the heavy particle recoil, which of course is very unlikely, but we are looking at that subleading order in the expansion, so this can happen. Okay, so this is literally the flip of the diagrams that we saw there. Okay, so what about at the next order? At the next order, more interesting things can happen. So for instance, we can have this H diagram, that we drew in the past. So let me draw it in a suggestive form. So for instance, by doing the usual trick of averaging over the momenta, I can think of it as this light particle, which emits some single gravitational wave or graviton that interacts with the source and then comes back. Or there can be more complicated things. So for instance, if I look at the ladder, so remember, for the ladder, we had to go to sub-subleading order to find a classical correction, which means we need to add 2 dots somewhere. Right? So if I add both dots on the bottom, we're back to the probe limit. So we need to add 1 dot in the bottom, 1 dot in the top. Okay? Meaning that what we have is the light particle, which interacts with the 1/r potential, and then emits a graviton that makes the heavy guy recoil, and then it comes back. This is 1SF, yes.
Again, why? Like second order deflection, correction to deflection, like particles. Why not?
It's at 0SF, right? Like this diagram here. This will have 2 inverse powers of 1/m, right? So it will have. Yeah. So I'm using the dot generically to denote a power of q over the mass of that particle, right? So for instance, okay, let's do the counting for this, right? Okay, so we had 1, 2, 3, m to the 6, 1, 2 over m squared, right? And then we had 1, 2, 3, but then because we have dots, right? So this is m to the 6, but now we are going to have m to the 4th, right? Because we have each one of these inverse propagators would come with a 1/m, but we're looking at the subleading order, so there's another one, right? So this goes like m to the 4th little m squared. Okay? Now let's do the counting for this. So we start with the same thing, right? So on the heavy guy, we would have m to the 6 from the vertices, but now we have 1/m from this, and then 1/m squared from this dot. And then on the other side, it's completely symmetric, right? So I would have. So this goes like m cubed, little m cubed. So it's indeed symmetric, and it's the same as m to the 4th m squared times m/m, which means that it's 1SF. Whereas this was times 1, which is 0SF. Okay, more questions? Yes?
How do you equate having particles like in the
Yeah, it's using the same trick. I just erased it, but you average over the labels, so you can identify that you will have always delta functions, so that you can think of them as.
Even we use the subleading propagator here. Yeah.
No, this is that's why I didn't write it as a source here. So this is more complicated. That's why I'm keeping it like this. Yes.
Maybe when you said about thanks. When you said before about that you could expand around Schwarzschild also to do this a bit more efficiently, how would you do that actually with amplitude since we are not in flat space?
Can you say that again?
Yes. What would be the connection with the amplitudes now that you are not in flat space?
Well, you can still compute amplitudes in a perturbative background, right? So we are still in flat space. It's just that it's a background which has like small perturbations around flat space, which we know to all orders. So you can think of it, I mean, you could think of it as scattering in some asymptotically flat space or just in some perturbative background which is just flat space with small corrections. Yeah.
Oh, okay, thanks.
Okay, any more questions? So what's the general pattern here? So we already drew a bunch of diagrams. So what's the general pattern? The general pattern is that only two things can happen. So what we have is this light particle, right? Okay, so let's contrast what happened at 0SF. So at 0SF, what we had is a light particle traveling and then interacting a bunch of times with the heavy particle that had generated some background. Right? But notice that this background interacted at a time, just once at a time with the particle. Okay, at 1SF, something new can happen. Actually, there's only two options. So you're going to have this particle, which maybe has been deflected a few times. So we have a geodesic, right? But then at some point, this geodesic might feel heavy, finally, and then emit some gravitational wave that eventually will come back. And that itself can interact with the background. Okay. So basically, this 1SF order, okay, and the other thing that can happen, which is very similar, is the same thing. So we have just the geodesic traveling in this background and recoiling over and over again. Now I'm drawing a curved line to just denote that it's actually moving along some trajectory. And then this might go and make the background recoil, the heavy guy recoil. It might move a little bit, the heavy particle, and then come back. Okay? But that's it. Then it can continue deflecting. So 1SF order is essentially a one-loop self-energy correction. So that's why it's called a self-force, because everything that's happening is that the particle now, it's emitting this, so it's exerting a force on itself, but it's a single graviton that comes out and interacts with the particle. It can either interact with the background or make the heavy particle wiggle a little bit, but eventually it's going to come back, and there's only one loop. Okay? So you can imagine what the pattern will be. So if you want to go now to the second self-force order, okay, you know now the power counting rules. So in principle, you can take any diagram and just figure out which particular term in this diagram will give me the self-force correction that I want. Or you can stare at this and say, okay, if I want second order self-force, I will have to have either like two loops of these gravitons that go and come back. So it could be something like, okay, so let's, just for fun, so this would look, for instance, like something like this, or something like this. So it can also make the thing recoil multiple times, etc., etc. Okay, but I need to have two loops of these gravitons that go and come back on itself. And for instance, a diagram that could have this, so these enter at high orders, it could be, okay, either now that diagram with the two dots on the heavy guy, which would be an example of this, or a genuine 2SF diagram only enters actually a 4 PM order, so 3 loops, and it would be something like this. I have the light guy, or now I have something like this interacting with the heavy guy. So this is like, so this is like a genuine 2-loop diagram.
A question?
Yes.
Just to clarify, by drawing the light particle flow line as a curve, you're taking into account the dotted line on the.
Yes, yes, yes. Yeah. Yeah. So, but this can also be like the leading order typically can be undeflected. So this diagram, for instance, it contributes already to the leading order. So the deflection, you just need to, typically you need to include them when you have like a 1/r. like a single graviton hitting, that typically that you need to go to the subleading order. Otherwise, you would get the free level times something.
Quartic interactions or suppressed?
No, in fact, I mean, this actually has a same counting. So remember back in the first lecture yesterday, I said that because these graviton loops, every vertex has a 2 derivatives, which is the same as the counting of a propagator. I can always pinch graviton legs for free and not change the power counting. So for instance, this diagram is actually has exactly the same counting as this, for instance, or as this. So I can always draw the simplest diagram or whatever one I like with the graviton loops to power count because they all have the same power counting.
And also at this point, you are considering also quantum contributions, or now that, because I mean, I see this, for example, now the very first diagram you drew a two-cell force. I see this kind of closure. I wonder, is this still classical or?
This is all, now I'm not writing any more quantum diagrams. Okay. There can be quantum corrections to these things also. But I think it's already complicated enough to understand the classical contributions, yeah.
So that type of diagram that you have drawn in the top, so I mean self-interaction. So for the 3-point vertex in one SF also there could be a self-interacted vertex, right?
Self-interactions?
For example, in the right-hand side figure, so one graviton line can go and hit the other one, right?
Ah, you mean
rather than the heavy mass?
You mean this one?
No, not related to heavy mass, but the self-interaction from the small particle.
This?
Yes.
Well, that's the 2SF is this effect here. You could have that twice. Yeah, so you could also have, for instance, this. And that would also be coming at this order.
Yeah, maybe I will ask you later.
Radiation gravitons and potential gravitons.
So that's going to come next, yeah, when I discuss the velocity. Okay, so I only have 20 minutes, so I better get to it. All right, so the last part of the course is just going to be to discuss the other expansion, which is the PN expansion. How do we think about it in these amplitudes? So we're going to use this method of regions once again. Okay, so this is kind of and as it was just mentioned, the key idea here is that we need to recognize that there's two types of graviton modes that can be exchanged between particles, depending on how their components, the components of their momenta scale with the velocity. Okay, so for instance, okay, we already know that we have these particles, which were the external particles, which were hard. So we have that they're like as large as their mass, and then in principle, their energies can be order 1 because they can just be like the mass, and the momentum is suppressed by their velocity. Okay, so these are the simplest ones that we understand that, okay, so this is the 0th component, and these are the ith components of the momentum. Okay. Okay, we can also have gravitons. So we know that the gravitons are of order q, but now we need to think about how their components scale with the velocity, and there's going to be two options. Okay, so there's going to be the option where the energy is suppressed by the velocity, and the free momentum is not. Okay, so this is actually pretty common, right? So for instance, if we have some non-relativistic particle, some massless particle, which is low, so the energy goes like one half of v squared, whereas the momentum goes like v, right? So it's not kind of uncommon that the energy for small velocities can be smaller. Okay, this is a massless particle, so it's a bit different, but this is the idea. So this is called the potential region, or potential gravitons. And you'll see in a second why this is the case. And the other option is that both components are suppressed. Okay, and this is called radiation. Okay, so why is this called radiation? Because both L0 and Li are suppressed by V. This means that these modes can be on shell. Okay, on shell needs to satisfy energy squared equals momentum squared for a massless particle. Notice that for a potential graviton, that can never be true. These modes are completely off shell. That's why they are mediating just potential interactions. Okay, whereas these guys are on shell, so they can radiate away. Yes.
That's the first order which are the higher operation.
Yes, that's right. Here we're looking at the leading scaling, yes. Indeed. Okay, so let me just say that in an equation. So these potential gravitons why do we call them potential? So let's look at the propagator. So the propagator is 1 over L squared, which is the same as L0 squared minus L vector squared. And then if the energy is much smaller than the free momentum, I can expand it away, order by ordering velocity. Right, so at the leading order, this will go like 1 over minus L vector squared, right? And these are going to be corrections that go like L0 Okay, so what are some of the properties of this? Well, so first of all, this gives me instantaneous interactions. Okay, because if now I do the Fourier transform of this thing, this is analytic in the time, in the energy. Right? So the Fourier transform of any one of these terms is going to give me inverse powers of 1 over r coming from the spatial part. But then the Fourier transform of the energy is just going to give me derivatives of delta functions at 0 time. Okay? So the Fourier transform of something like L0 to the n is going to be like derivatives of delta t. So these are instantaneous interactions. Okay, so what are the other properties? The other properties are that these potential gravitons, they always mediate interactions that are time reversal even or conservative. Okay, and that's because you see that here I have even powers of time. So these always give me things that will give me time derivatives squared. So if I integrate by parts, they would be given things like even powers of velocity. Okay, so this is always powers of v to the 2n, or another way of saying it is L0 when like v, so these are always powers of even powers of velocity. Okay, and also as I mentioned, these are off-shell, which means that cannot escape to infinity. And that's why we write them as a potential. So the point is that when we write a potential in quantum mechanics, okay, in quantum field theory, we always have particles that propagate, et cetera, but in quantum mechanics, we write potentials. So what are we doing? We're just integrating out these potential gravitons, right? So if these modes are on shell, these are not particles that I can produce, so I might as well just do the path integral over these modes, right? So whenever I have a diagram where I have some potential graviton, then I can just integrate them out and write this as V of R. So this is what we do typically when we write potentials. Okay, and also let me make another comment. which is that these, most of the time, they mediate the leading interactions. So why is that? So I was telling you that a lot of the times we can play this game of averaging over energies, et cetera, to see that sources are static. But actually, it's much more than that. So for instance, let's look at an example, this triangle diagram that we are by now very familiar with. And let's look at the propagator that we had here, P, 2P dot L, right? So if we declare that these gravitons are in the potential region, then I can expand away their energy. So this will just give me L. Okay. And now, in order to have something interesting, okay, so I have two options. So P, we said that it scales like 1V, right? So if I had a graviton which is in the radiation region, which has also 3 momenta which are suppressed by V, then I would expand this away completely and get something which is scaleless. So the only region that contributes here is now when L is of order V1, so it's potential, so this has homogeneous scaling in velocity. But then this thing is very simple. This is 1 over the mass and something like 1 over the frequency of the graviton minus the velocity of the particle times L. And because now these guys I've expanded away, this is the only thing that depends on the frequency, so I can trivially compute the integral of the frequency just by computing a residue. So indeed, I see that this fixes the frequency to be of order V, right? And then this just gives me these static sources again. So these are just potentials. Okay, so this gives me something very familiar, because then this will be a trivial integral of like which now just looks like some bubble kind of integral. Okay, and this also tells you that I need at least 1 matter propagator per loop in order for these integrals to be not scaleless. Okay, so I promise you that by looking at these velocity regions, then we could easily get rid of these quantum contributions. So let's look at our favorite quantum contribution, which is this, this loop here, right? So this loop just looks like V for L, L squared, L minus Q squared. But if I expand these gravitons in the potential region, then this is going to give me something like this. But now the integral over omega, it's scaleless. Now I can close the contour without picking up any residues. So this is just exactly equal to 0 in the potential region. I don't even need to worry about it. Okay, and the same is true for these other culprits that I was complaining that they're confusing, because if I look at this, then I might worry that this is classical, because as far as the Q counting goes, this looks like a classical contribution. But then again, this graviton loop, the simple velocity counting tells you that actually you can check that in any of these classical regions, then this will vanish. Okay? There is yet another region which I hid from you, which is when the momenta of the graviton doesn't scale with the velocity at all. That's the quantum region. So if you want to reproduce the full integral that will give you the full quantum amplitude, then you need to include also gravitons whose energies and 3 momenta are not suppressed by the relative velocity between the particles, but those are quantum. So by doing this simple region analysis, we can always keep these classical things. Okay. Yes.
Why did we draw the 1 over omega minus L factor?
Yes.
Why did we ignore
Here?
the rewrite integral, right?
I didn't ignore. I just computed a residue.
I understood the
Yeah, maybe I should have written 2 pi I here.
Okay.
Yeah.
When we do the floating constant wave, we make a lot of the space with that.
Yeah.
Now, which means that also including the quantum part.
Yes.
If I do this thing and I expand the
Thank you. So if I take, I just don't see clearly why integrating in this region would necessarily give you something quantum, because someone could say, couldn't I get a cancellation again from something else which is super classical?
So, I mean,
What do you mean by quantum? In quantum, in which expansion? That's what I don't understand, I think.
well, I mean precisely this, which means that all of these things that could interfere with classical things because they just have the right counting in Q, then if you just check these two regions, which is what we expect classically, we expect that these gravitons that we have are radiated by these point particles which have some velocity. So they're either like potential or radiation. They cannot be very hard. They're always suppressed by the velocity, right? Then things like this won't be allowed.
I agree, but then we also call quantum the subleading parts of parts that were classical in some order, and then when you expand them in higher order, they can interfere and indeed give you classical contribution. So we also call them quantum sometimes.
We also call quantum.
We also call quantums parts of amplitudes that lead to classical effects but are subleading in the Q over M expansion.
Yes, I mean, so those quantum contributions, right? You need to analyze them in detail, right? So when you have a classical diagram where you expand that subleading or enough order can lead to something which is quantum, right? Then those you have to be more careful. But the comment about these regions is that the ones that have classical Q counting, this velocity counting automatically kills them when they are quantum.
So the 1-1 will correspond to this type of diagrams.
Yes. So this is not 0 in this 1-1 region.
Okay.
And then it gives some non-trivial contribution.
Right. Thanks.
In fact, notice that this is the only thing that this can know about, right? Because this doesn't really know about the relative velocity. It has never learned that these particles have a velocity because it needs a propagator for this particle, right? So that's why all of these diagrams where you have loops that don't know that the particles have moved automatically will be quantum, and they're killed by throwing away this region. Okay. So just to write what I just said in words, this velocity counting, it allows various things. So it allows identifying quantum contributions that I can just drop. I don't need to worry about them. It allows isolating kind of the desired dynamics. By this I mean conservative versus dissipative. So I told you that if I just have potential gravitons floating around, I cannot have any dissipation. And then the last comment, and I will explain this in a little bit more detail now, is that it even helps identifying these classically leading corrections. These things that were like the higher powers of something classical. So these higher powers of classical contributions, which we were fighting hard to eliminate earlier. So why is that? So the same way that we can count velocity, the same way that we can count q's, given some diagram, we can very easily count velocity using these rules here. And for instance, this box diagram, okay, so which is our other favorite diagram. So let's count how it scales with the velocity, right? So okay, so as before, we have before L, we have L squared, L minus Q squared, to P1.L, to P2.L. Okay. Okay, so this example shows that these matter propagators, they scale homogeneously with the velocity, right? So we have that omega graviton frequency scales like V in the potential region. The momentum doesn't scale, but the external particle's momentum scales with the velocity. So each one of these is going to give me a 1 over V. The graviton propagators, we can expand in the potential region. So at leading order, I just have the spatial part, which doesn't scale. And then the measure, I'm going to have the energy component that scales like V, and then the three momentum components that don't scale. So this goes like V. So the power counting here is very simple, and it tells us that this diagram scales like 1 over the velocity. So it's actually singular at slow velocities. Whereas all of these classical quantities that we like to compute actually have a well-defined velocity expansion. Okay, so whenever we look at the amplitude and we see some piece that goes like inverse powers of the velocity, which we can easily identify using this velocity counting, we can be sure that this will exponentiate into something else. Okay, so we don't need to worry about it. So in contrast, this triangle, it just has, okay, so these don't scale. The measure has 1 power of velocity, and then this has an inverse power of velocity, so this scales like velocity to the 0. So this is not singular, so it will be fine, yes.
But if you have some diagram of some loop order and you find that it's 1 over V, someone could still say, oh, but you can expand it, the next order is at the end, the order is unit, and maybe this will contribute to each other.
It is true that this could have pieces which are not singular, right? But the point is that the full answer as a function of velocity will be singular. So if we're doing really the Pn expansion, then we can be sure that this whole, at least the singularity needs to cancel. So at least there's something here that has to exponentiate. And typically it's the whole thing. Yeah.
Can you make this side into 5 loop orders, or?
Yeah. Higher loop orders, okay, so what's the novelty at higher loop orders? So the other thing is that this argument that I made here, that we can, whenever we have this matter propagator, okay, we could always play this game to put these delta functions here, right? So what does this mean? The fact that whenever we had here. So given some diagram, this was also useful when we were thinking about the mass counting, thinking about the static sources, right? So whenever we could play this game of averaging over the momenta to put various legs on shell, so we had things like static sources, maybe with something else. So what did this look like? These propagators here always look like delta P dot L. And that automatically puts L in the potential region. Right? Because this is telling me that, okay, we know that P, so this is telling me this goes like the mass, and then omega minus V dot L. So this is always setting the frequency of the graviton to be of order velocity. Right? So all of these diagrams, we always know that they're in the potential region. So for instance, at one loop, you can check that all of the diagrams that we drew, we could always play this game on one side or the other, so they're all in the potential region. In fact, the first time we can have something which is radiative, it's at 2 loops. So what does this look like? Getting tired, or the board is becoming heavier? So at 2 loops, we could have things like this H diagram, where on one side and the other, we can play this game of putting static sources. So we could have these legs being in the potential region, but now this leg here can be in the radiation region. Okay, or similarly, we have these diagrams that look like this, for instance. And again, this will be potential, this will be potential, but then these guys are not completely on shell. So this can be in the radiation region. So it's only at this order in the PM expansion that we start to see the first radiative effects, as you would expect, because you expect the radiation starts when you have like a 2 to 3 process, right? Which is kind of the cut of this 2-loop amplitude. Okay, and then the last rule, if you want to try to draw these diagrams, something to keep in mind is that whenever you have graviton interactions, or interactions of gravitons with matter, in order to draw a diagram which is allowed, you need to conserve momentum at the vertex. Okay, so for instance, this is allowed because you can have 2 potential gravitons, right? So potential gravitons will have moment, like things that go like V1, V1, right? So this is potential, potential. And then I could have some radiation graviton coming out here. Its momentum scales like V. So this kind of process is allowed because I have that there's a big component here of the 3 momentum that just goes through, and then there's a small correction coming from this. But for instance, I couldn't never have a process where I have 2 radiation gravitons and 1 potential. Why? Because the radiation goes like V, 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 but then the potential goes like V1. Okay? So where does this big 3 momentum go? I need to conserve momentum at every vertex. So this thing actually is not allowed. Okay, so now you can have fun also trying to draw diagrams and trying to identify which gravitons actually can be radiative or can be potential. So typically, whenever a graviton can be radiation, it can always be potential, because I can always have like a bigger 3 momentum, but not vice versa. Okay. Okay, so I think we are basically out of time. So let me just comment at the end. So hopefully I convinced you. I didn't have time to talk about observables, so kind of half of my grand plan wasn't realized, but at least I convinced you that all of these things that we know for kind of classical dynamics, all the different expansions that people have looked over the years, and that we use to solve classically Einstein's equations, they can all be kind of easily understood from the point of view of scattering amplitudes by just taking diagrams, expanding in the right way. So now, whenever you want to understand the origin of some effect, you can very easily at least power count. So notice that I think the only diagram that I computed in all of these 4 hours of lectures was this 3-level exchange. Actually, I didn't even compute it precisely. I didn't write the numerator. But this at least shows you that you can go a long way and understand many things just by writing twiddles instead of equalities and just power counting various diagrams. Okay, thanks a lot.
Any further questions before we close the session?
Yes.
I'm a bit confused because I thought the H diagram, like the 2-loop diagram you drew there,
Yeah.
If we're doing exponentiation and subtracting the cut, then the radiative part would be subtracted off.
No, so this thing, so it is true always that the imaginary part that has a graviton comes from radiation, But as for instance, I think Sebastian mentioned in one of his lectures, whenever you have an imaginary part of an amplitude, this always implies by analyticity, et cetera, that there has to be a corresponding real part. Right? So for instance, this diagram here, where even I computed in the potential region, it won't have an imaginary part, because this graviton cannot go on shell, right? But in the radiation region, it will have both a real and an imaginary part. So when you take the log of the amplitude, that will achieve, the job of that will be to cancel the imaginary part, but there's a remaining real part, which is physical, and actually that's, for instance, what encodes the radiation reaction to the motion of the particle. So it doesn't come from the cut, it comes from the real part of the diagram, which also would have a cut.
There are no more questions. Let's thank Julio again.